All right, section 4.2. Hello. And here we go. We got into experiments. So, understanding the difference between an experiment and an observational study. We got into confounding all the vocab that goes with it, experiments, the different types of experiments, what is statistically significant. Lots here. Dense, very dense. Okay, so observational study versus experiment. Observational study, you're observing. We're not attempting to influence the results. We're not controlling for anything. In an experiment, we're imposing a treatment. We are controlling something. That's the difference. All right. Confounding. This is something that can happen in experiments, or it's the reason for an observational study you cannot conclude causation. So this could happen in experiments or observational studies. So let me give you a diagram. There was an AP question once I'm thinking about. I think it was an observational study, but it was like they wanted to know the number of apples that you eat and the number of cavities. I don't know how to spell cavities, so I'll just abbreviate. Number of apples that you eat and what influence does that have on the number of cavities that you have? Well, you start thinking about this like, okay, maybe people that eat apples are just healthier in general, and healthier people brush their teeth more, so they have less cavities. So now I wanted to say that is the number of apples eaten causing you to have a certain number of cavities, or was there an association? But now I have this other variable, people's overall health. Like this is there has to be an association with the response, the explanatory variable, and it has to also be connected with the response variable. I don't, RES. Oh my goodness. RESP, response, go. So there's an association between the number of apples eaten and if somebody's healthier or not. They might just be eating healthy. So that's why they eat a lot of apples. And like I said a minute ago, healthier people might be brushing their teeth more. So now we don't know if it's the number of apples eaten that's causing them to have less cavities or the fact that they're healthier and they have these other habits that are causing them to have less cavities. So we're confused. We're confounded. This is a confounding variable. This is bad. We want to be able to say that A caused B. That's ideally what we're going to do. So we try to control for those in an experiment. And we can't control for them in an observational study. Hence, we can never conclude cause and effect. All right. This is fun. I hope you're enjoying this. So in experiments, we get to the language of experiments. So a bunch of vocab here. Treatment, experimental units, subjects. So treatment is what you're imposing on your subjects. We use the word subjects if it's human beings, experimental units if it's animals or if it's things. Okay, you can have an experiment that has multiple explanatory variables. If that's the case, we start calling those factors, and each factor has a level. So let me give you an example. Say we're testing some laundry detergent, and we're just checking the cleanliness of the clothes. So there's a couple different things that I might be checking. I might be checking how much laundry detergent. So let's say we have a control group 0, maybe a half a cup and 1 cup of laundry detergent that we put into the wash. And the cycle of the washing machine, say it's high, medium, and low. I don't know. Actually, I'm going to do this medium, high, medium, low, and low. Okay, so this is an explanatory variable, the amount of laundry detergent. This is an explanatory variable, the cycle on the washing machine. Because there's more than one, we call them factors. So in this case, there's 2 factors. One is the amount of laundry detergent. I'm just going to abbreviate. This has 3 levels, 0, a half, and 1 cup. The second factor is the temp on the washing machine, and this has 4 levels, medium hot, medium low, low high. I don't think it was temperature. I think it was just like cycle, but there's 4. So how many treatments are there? It's all the possible combinations. So it would be like 0 with each of these 4, or 1/2 with each of these 4. So there would be an overall amount of 12 treatment groups that we would need to consider. All right. How to experiment badly. If you don't have random assignment and you just let subjects choose which treatment group they go into, that's a problem. If you only have one treatment group, that's a problem because you have nothing to compare to. So there's certain things we have to do to have good experiments or to experiment well. We have to have comparison, meaning you have to have at least 2 treatment groups. One could be a control group potentially. It doesn't have to be. You have to have random assignment. So you're randomly assigning how your subjects or experimental units are assigned to the groups. Typically, we do that with the HAT method or just explaining how we're going to do that using like technology. This gets into the HAT method a little bit here. So there's 4 main pillars of experimental design. 1, comparison. 2, random assignment. We talked about that. The random assignment, let me go a step further. The reason behind it is we're trying to create equivalent groups. That, like, if we think males and females, old and younger people are going to respond differently, it's like going to make sure that males and females end up in each group and older, middle, and younger age people end up in each group. So it's balancing out those effects. Okay, we need to control. This does not mean we have to have a control group. This just means we need to control all these potentially confounding variables. So if I'm giving somebody a drug for cholesterol, and I think the amount of time that they exercise and how many calories they intake each day is going to have an impact, I want to control for that. So maybe I create 2 groups, like those who exercise, those who don't. Or I just say, all right, everyone, you can exercise for 20 minutes a day. And everyone does that. I want to keep everything else the same except the treatment, in this case, the cholesterol medicine. Replication, that means you have multiple subjects in each treatment group. Why do we do that? Because if one person's cholesterol drops 60 points, we don't know if that's an anomaly or if that's like a general trend. So we have this replication happening. So if 20 people on average have a 60-point drop, like, okay, now I think it might be the drug and not the fact that it's just an anomaly. All right, well-designed experiments. The very base level is a completely randomized design. You take your subjects or experimental units, you randomly assign them to your treatment groups, however many there are, 2 or 3 or 4, etc., and then compare the response variable, whatever you're measuring, within those groups. We talked control group. That's a group that does not get the treatment. So it could be a placebo. Ideally, you want to, I might as well get into this idea. A placebo is a treatment that looks exactly the same as the regular treatment. Typically, it's a pill. Pill looks like the real pill, but it's just the sugar pill. So people don't know if they're getting the real treatment or the fake treatment. That's called blinding. And an experiment can be single or double blind. Single blind meaning the subjects do not know which treatment they got. Double blind meaning the subjects and those evaluating the response variable. So maybe it's like measuring your cholesterol when you're done. Like they don't know which drug you got. If both of those parties are blinded, we call that double blind. The placebo effect. That's when we watched that video, Whiffed, I think it was. It was like this fake energy drink, and they were out on the beach, and the guy was like hitting the thing with the sledgehammer type thing and trying to hit the bell on the top. Like he thought he was getting this energy drink, but he really wasn't. But he did perform better because of the placebo effect. Double blind, we talked about that. It can be single blind if one of those parties, either the subjects or the people evaluating the response, don't know which treatment was given. Then we moved into statistically significant. And that's a fancy way of saying our results probably didn't happen due to chance. It was probably due to the treatment, whether it's the drug or the exercise program or the food that people are eating, whatever it might be, the type of laundry detergent that I used. That's what we're trying to answer. All right. Oh, yeah. Okay. So then we got to a stronger type of experimental design. We have completely randomized, which is like that base level. Then this idea of randomized block. What the heck is blocking? So if I am giving this cholesterol medicine to people and I think males and females are going to respond differently, I don't want to leave that up to chance. I want to control for that. So what I do is I block my experiment based on gender. So what I mean is this. I'm going to take, say I have 50 people, and let's say there's 30 male and 20 female. I'm going to split them by gender or by sex first. I'm not leaving that up to chance. And then I'm going to randomly assign half the males to the, let's say, the drug and half the males to the placebo. Same thing with the females, randomly assign half the females to get the drug. That's D for drug, and half to get the placebo. This is a randomized block design. Completely randomized, I would just take these 50 people, 25 get the drug, 25 get to the placebo. But the issue is now the person's sex might be having an impact on their cholesterol level. So that's randomized block design. You can see that modeled here. Okay, then we went on to this special type of block design called a matched pairs design. And this is ideal if you can pair two subjects that are very, very, very identical. So if I go back to the gender thing, maybe I think age is a factor too. So I pair two females that are almost the same exact age together. And I do the same within the female group and the male, just pair them out by age. And then I randomly assign one of those two people to get the drug and the other to get the placebo. So now I'm taking out all this variation that could occur due to age, and maybe I just have like a 51-year-old female and a 52-year-old female, so they're essentially the same in terms of age, and I've controlled for that. The other idea of match pairs is each subject gets both treatments. So if you remember, we did a question about waterproofing boots, and we wanted to see, like, is the new waterproofing method better or the old? Well, different people walk outside at different times depending on their jobs. So what we said ideally is I'm going to draw some boots. It's going to be terrible, but it's going to be fun. There's boot one. I don't know why I'm making the noises, but it's fun. There's boot two. So boot one might get the new spray and boot two gets the old spray, because now I've gotten rid of all that variability from one person to the next, and it's just where your left foot is walking and where your right foot is walking should be pretty similar conditions. That would be a matched pairs design. Each subject got both treatments. So that's matched pairs design. Let me see if there's anything else. No, that's the end of section 4.2. A lot here, a lot of vocabulary again. Hope you found this helpful.